The CAP theorem, also known as Brewer's theorem, is a key principle in distributed systems, stating that it is impossible for a distributed system to simultaneously guarantee consistency, availability, and partition tolerance fully. A system can satisfy at most two of these three characteristics at the same time, but not all three. Consistency means that all nodes see the same data at the same time. That is, all read operations should retrieve the most recent write data. For example, if one node in the system receives a write operation, the system needs to ensure that all other nodes also receive this update in sync to maintain data consistency. Availability means that the system is always able to respond to read and write requests, even if some nodes fail. A system is considered available if it provides a non-error response to a request, although it may not guarantee the latest data. Partition tolerance refers to the system's ability to operate despite network partitions. When network issues arise and nodes cannot communicate with each other, the system can still function. In distributed systems, network partitions are unavoidable, making partition tolerance an essential feature for almost all distributed systems. According to the CAP theorem, no distributed system can simultaneously ensure consistency, availability, and partition tolerance. It can only satisfy two of these three properties. Since partition tolerance is almost essential in distributed systems, system designers typically face a trade-off, ensuring consistency and partition tolerance (CP) while sacrificing availability, ensuring availability and partition tolerance (AP) while sacrificing consistency. HBase is an example of a CP system, meaning it prioritizes consistency and partition tolerance. During network partitioning, HBase may reject certain requests to ensure data consistency is maintained once all nodes reconnect. For example, if a write operation occurs within a partition, HBase will ensure that all nodes reflect consistent data, even if some nodes become temporarily unavailable until the network is restored. Advantages: strong data consistency, with each read-write reflecting the latest data. Disadvantages: when network partitions occur, some nodes may be unavailable, reducing overall system availability. Cassandra is a typical AP system, prioritizing availability and partition tolerance. In case of a network partition, Cassandra continues to handle read-write operations without requiring all nodes to be in sync. When the partition ends, it reconciles inconsistencies in the background, achieving eventual consistency. Advantages: in large-scale distributed systems, even if some nodes lose connectivity, the system remains highly available. Disadvantages: reads may return outdated data until the system eventually reaches consistency. Traditional relational databases like MySQL typically ensure CA, consistency, and availability, but lack partition tolerance. Their design assumes reliable networking, allowing them to provide both data consistency and high availability. However, if a network partition occurs, the system may go offline entirely, ceasing to provide service. Advantages: strong consistency and high availability when no network partition occurs. Disadvantages: when network partitions or communication failures happen, the system may become entirely unavailable. In real-world distributed system design, developers often need to make trade-offs among the three CAP properties based on specific business requirements. Consistency. First, when data consistency is critical, such as in financial transaction systems, a CP system is often chosen to ensure that no inconsistencies arise even during network partitions or failures. Availability first. In systems with high availability demands, like social media platforms or streaming services, AP systems are preferred to maintain high availability, even if data may be temporarily inconsistent. Eventual consistency. To balance high availability with consistency, many systems, e.g. Dynamo Cassandra, adopt an eventual consistency model. This approach ensures that while the system remains highly available, all data will converge to a consistent state over time. This compromise is very common in distributed systems. Thanks for watching. For more information, please visit bowsy8.com.